So this is lecture 4 of 2025 about tangible incompleteness by Harvey Friedman, please.
Thanks. Okay, so I think I've got the idea of how to proceed here. Uh, uh, there's a certain level of detail that we're going to do today, which is not the ultimate level of detail where you're actually literally checking everything. I mean, or something like that. It's just too involved. But there's a certain level of detail here on just this section 411, which we agreed on doing. Um, and um, and what I will do after the lecture is do a final proof checking of the manuscript 411, chapter 4, section 11, um, and then put that final version on my downloadable lecture notes section. My downloadable manuscript section, which already has sections 4.1 through 4.5. On the downloadable lecture notes page will be this particular thing that I'm talking right here, maybe lightly edited. This way, when we go through uh, these sections in the reversal, I will also be completing the final version of the chapter and putting it up on downloadable manuscript. So everything will be done. I'm expecting this book to be done, finished in final form, the whole book in by the end of the summer. Uh, because there's other important chapters in it. All right, so uh, and various polishing has been going on, particularly in section 3, which is the positive part. We're not talking about section 3, we're talking about section 4, chapter 4, sorry. One of the things is a change of notation from less than 0 to -10, which is the same meaning in the statement that we're reversing. This is to make the transition from the core mathematical section, chapter 2, to make the transition from there to invariant maximality as smooth as possible, because that's the notation I currently use for chapter 2. So you want basically the same kind of invariance for both, for same invariance for the core math and for the logic. All right, so recall that this is the reversal structure, these 11 sections. And today we're going to talk about 411, how that goes, with a reasonable amount of detail. So section 11 starts off with the end of section 10. And this is an abridged, semi-formal version of Theorem 410.27 from the text, which I put a bunch of English in and some comments and cut out some stuff in order to make this more understandable. So this is the starting point. The starting point is the fairly late thing in section 10. That we have a structure W, D less than capital P set epsilon. This is a second order structure. Constant C1, C2, dot, 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 and functions $1, $2, dot, dot, dot. And I want this to be satisfying a set of sentences in L of W. So I don't insist that C1, C2, dot, dot, dot are unbounded, because that wouldn't be a sentence. You see, that wouldn't actually be a particular sentence. So we're not going to assume that it's unbounded. We don't need that it's unbounded in D. So this is all some first order theory. Now, how does this work? Set is a family of subsets of D, as you might imagine. this is a second order structure. Of course, everything's countable. And we've already done section 10 up to now. I mean, we didn't do it, but 410.27 is the last thing in the section that does it. Namely, we've already cut down to the constructible sets, the constructible subsets of D. So the idea, just idea, is that set is really the family of constructible subsets of D. So you know what's going on here. Less than is a strict linear ordering on D. And remember, we were agonizing over the fact that for a long time in this reversal, the domain is densely ordered. We're way past that in section 10. It's internally well-founded, as discussed down here, W well order. Okay, extensionality for the sets. The C's are strictly increasing, and they're kind of indiscernibles from D, explained lower down. Now, the dollar signs. The dollar signs are functions from set, from the whole of set, in fact, into points less than or equal to C of n. And it's 1, 1 when it is less than Cn. Now, what's the idea here? The idea here is that only a bounded, so to speak, amount of set is going to be less than Cn. Only a bounded amount of set, so to speak. So in other words, this is almost always C of n, but it's only interesting when it's less than C of n. You see, and the idea is that $n is less than Cn just in case the set we're applying it to is in the constructible hierarchy up to level Cn, up to level Cn. But the constructible hierarchy is all buried in without talking about it in this in W. You see, we don't. This is all abstract. We that's all the shop, the work that's in section 10 is constructibility stuff. But this is the result of all of that. The value is always greater than the elements of the set. That's actually not quite right. The values when non-trivial, when less than Cn, when they're non-trivial, always greater than elements. Okay. The idea is that $n of A is like the ordinal index of A in the constructible hierarchy, if that is less than Cn and then Cn otherwise. In other words, like it's important in the theory of constructible sets that you have a well ordering of the constructible sets. You have a nice map from a constructible set to the ordinal, its ordinal, and make it 1, 1. Okay. In other words, it's the way it would be done most easily in set theory would be you pick the level in the constructible hierarchy, and the first order thing that actually defines it. But then, of course, you have parameters which also have their ordinal. Yeah. So all that stuff, is done in chapter 410, like it is done in set theory, in ordinary set theory of the constructible hierarchy. All right. Now, once you pin down the ordinal of A, so to speak, when you go up higher in the dollar sign, it's the same thing. Otherwise, this stuff is worthless. You see, the dollar signs give you, as the index goes up, more and more things get non-trivially handled. That is, $n plus 1 of A less than C of n plus C of n plus 1, is more sets than dollar $n of A being less than Cn, Okay. Dollar $n not being on true is very inconvenient. And in section 411, we fix this by getting surjective delta n's. So out of section 410, we only get these dollar $n maps. We only get them that they're 1, 1 in the appropriate 1, 1 when they're non-trivial, i.e. less than Cn. We only get that they're 1, 1. We don't get that they're onto. And this turns out to be a nuisance for things we want to do. So we have to fix that. That's the first main order of business in section 11. All right. We have a pairing function on D, and it's the unique pairing function given by maxlex. Maxlex, is orders pairs, well, n tuples, but say pairs only here we care about. Pairs first by the maximum coordinate and second lexicographically. So I call that maxlex. Maxlex, not lex max, maxlex. All right, now we have internal well ordering. Every non-empty set has a least element. And by set, I mean a member of capital S, capital E, capital T, right? Right, there we are. Right, S, set in capitals. Every non-empty set has a least element. Every set has a least strict upper bound. Remember, sets are just sets of points. Points are elements of D. Now, finally, we have separation and indiscernibles, and this is very important to have to be said right. So we have separation, not arbitrary separation, but separation when the first order quantifiers are bounded by D. Second order quantifiers are restricted to the A that are handled by $sign sub n minus 1. Right? Those the second order quantifiers are restricted to that. And the first order parameters are less than D, and the second order parameters are sets A captured below C n minus 1. Then the separation exists. The separation exists as a subset of and has $n value less than Cn. Okay, that's what we get from the work in chapter 10. And then finally, the indiscernibles have to be discussed. Here we say that if you have a formula and you fool with it a little bit, it has the same truth value. So there are going to be parameters in this formula. There are going to be parameters less than CR and set parameters below CR, meaning $sign sub R is less than C of R. Just set parameters like that. And we're going to have various C of I and dollar of I appearing. And the I minus R must be, and we're going to move these subscripts or indices. We're going to move these indices in an order theoretic way, in an order preserving way. The indices R through n minus 1 are going to be moved in an order preserving way. And the ones below are going to everything. All the ones below are going to stay the same, and these parameters are going to stay the same, of course. Then we get the same truth value. This is the right kind of. See, indiscernibility gets a little more involved when you talk about second order, but it has to be done right. If I kept everything first order in this reversal, it would be much too complicated. You would have strange things going on that that are impossible to decipher. So it's natural to go to a second order system, second order structure with this second order indiscernibility and this kind of limited second order separation. Okay. So now we are in chapter 11. I mean, excuse me, section 11, chapter 4, and it's appropriately titled Con SRP. And the first order of business is to show that theorem 1027 that we just discussed can be strengthened by adding surjectivity uh, to the clause about the dollar signs. This is going to require that we upgrade $n. Now, it's fairly obvious how you want to upgrade $n. You want to make sure that it's surjective. So what you do is rework it. Remember, we're just trying to $n just indexes with ordinals, quote unquote. That means elements of D. We're indexing by ordinals um, these sets. So we want to change the indices so that the set of ordinal indexes is is all of C of n rather than just scattered through C of n. Make sure that it's onto, right? That's what we want to do. And if we were doing regular set theory, we just say in one word, we'll just transfinitely collapse it, just rework, just reindex, right? But we have to be careful here because we want the reindex to have nice properties and be simple and all that, and we don't transfinite recursion is not an immediate thing here, so we need to carefully use separation and indiscernibles. This is a little involved, and I'm going to go through it pretty quick. Okay, the first remark is this is important, and this is important also for power set. We're going to get models of set theory out of this. Okay, so power set is going to be essentially important here. So this is a kind of power set. If I have D less than C of n, and I have any subset of from 0 to D, and it's captured sometimes, somewhere in some M, these subscripts on these dollar signs are standard integers outside the structure W. Um, if um, if E is indexed somewhere, meaning it's constructible, quote unquote, then it's constructible by level Cn. In other words, we want to pull it down. We can assume M is bigger than N. Yeah. So and we have dollar sign of M of E is less than Cm, and dollar sign of N of E is Cn, and we want to derive a contradiction. Um, in other words, this thing gets constructed way later than it gets constructed right now, right? This kind of thing. As in Gödel's work on constructible on L and power set, that stuff, right? So we want to get a contradiction from this. So we make these statements that uh, there's somebody that's Cn. That's where we want to get a contradiction, right? There's somebody, uh, there's somebody, some A that can get constructed high up, uh, where it doesn't get constructed way down. Doesn't get constructed down means remember that it's C of n rather than being below Cn. Remember that's how the setup is. Well, then we can by indiscernibility we can cut M down to n plus 1, right? Because M is bigger than n. You can cut this back and replace M by n plus 1 by that's a form of indiscernibility. And then by another indiscernibility, we can uh, This should be this. I think this is wrong. This should be +1. We can add 1 to everybody here. Okay. And we can let 2 be hold, we can minimize the A naught. We can minimize the A for 2, and we can minimize the A for 3. And then we use indiscernibility to prove that we can minimize that both A and B, first of all, they're unique, of course, because we minimize them. And we can prove by indiscernibility they must be equal because these A's are subsets of 0D. So the indiscernibility kicks in, see, with parameters that are small. And you can't have A naught equals B naught here. You can't, that's not possible because we get different values here. Yeah. All right. Okay, so it gives you an idea how that's done. All right, so then there's another one. This says that if I have a function from 0D and D is small into 0CN, then it's bounded, and the function itself is constructible. That means that there's some m such that this gets less than Cm. And what do I mean by what do I mean by handling a function? I just mean handling the forward image of the function um, under the pairing function. See, we only handle one-dimensional sets here. It's only one-dimensional sets that are being handled. So you have to, if you have a two-dimensional set, which a function is, because a function is it's a graph identified with a graph. The forward image, you have to take the forward image under the pairing function in order to get a set. So that's why I write $m of power of p of f. That's not power set. That's the pairing function. Pairing function, the forward image of the pairing function on the function. Forward image of P on the graph of F. Forward image of P on the graph of F. Then it's bounded below Cn, and the actual thing is less than Cn. All right, and this is done by another tricky kind of thing where uh, you do something and then you raise the index and compare them. Uh, so you see if you have uh, yeah, you assume it's false and you get something with a sup as range as C, and then you automatically get one with a sup of the range as Cn plus 1 uh, by indiscernibility, because you can do this with n, you can do it with n plus 1. But then these are both nicely defined, and so therefore they must be equal. Uh, they can't they can't diverge like this with the sup of the range being that using indiscernibility properly. Everything this has to be done delicately, but anyways, so you get the bound, and then you get the actual thing by uh, by separation. You actually get the actual uh, thing because now the sup of the range is small. Okay, so you get this kind of thing. All right. So this is a bounding thing. Then you can now you want to do an enumeration. Let's go back to what the goal is here. Remember, I wanted to I had these dollar signs that they were only into. I want to make them onto. So I just have to collapse their ranges. I have to make their ranges and everything instead of just some things, and make sure the ranges is all the way up to the place we're working. And you can do that by enumeration. Of course, you have to show that when you enumerate it, it's still unbounded, but that's uh, easy to see. Although that, yeah, that's not going to be an issue. So the idea, so that's why we need this thing. So if you have uh, any set that's constructed before level n, so to speak, level Cn, then there's a unique order preserving bijection onto DE, an interval DE. Remember, we want to set it up so you start with it any place you want below Cn. For technical reasons, I think that's useful. So, and you want to make sure the bijection actually can be constructed. And actually, you can get the construction to be, um, you can get the length to be less than C of n for any one fixed set E. And also, the actual function itself is constructed, you see. So this calls for a transfinite enumeration of E as a function. And uniqueness is straightforward. And you take the least D prime in E so that you can't do this staying constructible for E intersect. You want to take the least D prime so you can't handle this for an initial segment. And that's obviously going to have to be a limit point. And then you take the union of the order preserving bijections that you just have. They all cohere. So we can do this for all of E, but we don't get the desired contradiction because this union is only constructed higher up. See, that's that's a problem because in order to get this set over here, namely the union of the order preserving projections, the bijections themselves, you have to say where they are in order to apply separation. So it climbs up on, that's a problem, right? But the contents are below C of n because you can use the indiscernibilities to show that the values are fine. No, we don't even need indiscernibility for that. The values are fine. So therefore, we can already use the previous lemma to argue that the actual function is fine, that the actual soup is below C of n, and the function actually exists. So you can get this with the help of 411.2. And then you can, since I know how to do transfinite enumeration, a kind of transfinite recursion, I can apply this to the range of $n. Remember, the range of $n minus the default C of n. That was the problem. The problem, this was not the interval from all the way. That wasn't covering everything below C of n. That was our issue, right? We want to make sure that we have an onto dollar signs, right? That's what we're trying to do. So this just applies the previous thing with some technicalities to make sure that things are set up right. See, we ultimately want to go from zero. Um, and we get this for the thing we just did before. Yeah. So now we have this upgraded dollar sign, I call it double dollar sign, which is defined by this collapse function, this collapse to an interval, this transfinite recursion, right? Uh, so we use what we just proved in order to define the double dollar sign. And now here's the point. Theorem 1027 holds for each $n replaced by double $n, and the clause regarding the dollar signs is upgraded with an additional surjectivity axiom that everything below Cn is hit by some double dollar sign of some double dollar sign, double dollar sub n of something. Yeah. This is just a D of one just means this is just a variable. I'm not using subscripts as much as I'd rather use this idea. Yeah, the one doesn't have any significance. It just means like X of one in predicate calculus or something, or V sub one. You know. All right. So we're going to use the double dollar sign instead of the single dollar sign. And then we have the following official improvement. Now, this time I'm not going to sugarcoat it with nice English. I'm going to state it the way it actually is stated in the text. There's a structure W, just as I said. We have extensionality. These are increasing. We have strict linear ordering and successor and least element 0. We have the stuff about the dollar signs here, except that this says there is a structure W. The answer is, how do we do this? We're going to set W, we're going to set $n, dollar sign, dollar sub n, we're going to set to double dollar n. That's why we're going to get this. This is a surjectivity. Well, this is something else. This was already present in the original one before we improved it. This is the improvement. Everything else is the same. We didn't change anything. We have our pairing function. We have internal well ordering. We have internal another kind, supremum. We have the same separation, the same indiscernibles. All right. By the way, we're way past using the parameter little k that we've been talking about. That this, that the reversal starts with an integer k. That's handled somewhere in early section 10, right in the beginning of section 10. We're only doing section 11, starting with the end of section 10, of course. All right, we now are armed with the improved $n. In particular, $n is a bijection from the e's that are handled by level n. This is a bijection, and we make extensive use of this bijection, the inverse. We make an extensive use of the inverse in the treatment. So we have a bijection, we can take its inverse, also a bijection, thankfully. All right, so here is the key construction that will throw us into set theory. EP, and EP is abbreviation for epsilon. Epsilon sub n is the binary relation on this interval given by d EPN of E, if and only if D is a member of $n inverse of E. Remember, $n of n inverse of E is going to be a subset of the interval from 0 to Cn, right open. So D is related to E if and only if D is an actual member of the set associated to E, associated by taking the inverse. And the inverse exists by the surjectivity. Remember, we set $n to be double $n, which is forced to be surjective. Okay. Now, we're going to show that each one of these things satisfies ZFC. So this is already something worth pointing out to in just pure set theory. So I'm going to make a digression here, maybe a memorable digression. Set theory can be defined as a bijection from the sets of ordinals 1, 1 onto the ordinals. The sets are the ordinals, and a first ordinal is a member of a second ordinal if and only if the first ordinal lies in the set of ordinals associated with the second ordinal. For our specific purpose, it was better to have the bijection from sets into ordinals. This avoided certain notational complications. But going the other way looks nicer for this digression. So we say, let's change the digression. It's trivially the same. Set theory can be defined as a bijection from the ordinals 1, 1 onto the sets of ordinals. Now, when I say sets of ordinals, I'm not including classes of ordinals. These are bounded. The sets are the ordinals, and a first ordinal is a member of a second ordinal if and only if the first ordinal lies in the value of the second ordinal. By the way, this is a way of talking about set theory with a definable well ordering of the universe. It really the definable well ordering of the universe is implicit in this way of looking at what set theory is. So this provides an easy way to go from flat set theory to set theory. See? So that's what we use here. It really avoids a lot of complication when doing this. A bijection from the ordinals 1, 1 onto the sets of ordinals, not classes of ordinals. That would be Russell's paradox. We would stay away from that. All right, now we're going to go through. I'm not going to do all these details, but I'm going to go through why this is a model of the ZFC. So what is a model of ZFC that I'm claiming to be? Once again, let's go back. This. This is the domain, and this is the relation. I'm saying that that's a model of ZFC. All right. Well, one thing we need that's important and useful is that if D is a epsilon E, then D is less than E. And this comes out of one of the things that we did in the setup that we already had in the hypotheses. When they talk about the structure W, that indices that the value of a dollar sign is bigger than all the elements of the thing that you're of the argument. It goes back to that. Extensionality comes from the fact that this is surjective. You get extensionality. Now we want to. Now this is important. This is a little different. This says if E is constructed by level n or level Cn, uh, there's a unique D such that every B less than Cn, B is a member of D if and only B is an E. Yeah, this is a form of separation almost. Okay. This is a form of separation enough to get pairing and union easily. Uh, Now, this one here is at the heart of how power set is going to come out. So yeah, so given any place less than Cn, I can look at all the subsets of that place. I can look at all the subsets of that place, and I want to find a fixed place also below Cn, such that everything is constructed by that level. And we already did something very close to that, if you remember, in 4.11.1, first thing we did. And so this is just carrying is just is essentially redoing that, putting that in this context. I mean, you have to do a little bit more work, but it's still, you can see it's basically all this. Oh, did I must have copied this. Just a second. Yeah. I copy. I bilemma 411. Copied it twice. Ah, I think this is what I did. Yeah, there we are. Yeah. All right. Now we want the inclusion relation. We want notation for the inclusion relation, which makes no sense for points, but it does make sense since we have a structure EPN. So there's an inclusion relation in the sense of the structure. I need that. So that's how we use that notation in order to even state power set nicely. And we get power set from the previous thing, from the previous thing that we did. We get the power set. Look, it's a very detailed thing, but the basic ideas I'm trying to state how they work. So we have power set, and then these are these are pretty straightforward. Choice becomes easy because we were all set up. We all set up things with this dollar sign thing so that everything is indexed by things that are internally well ordered. So choice comes out pretty easily. The same thing with and foundation also. Well, yeah, this is definable well ordering of the system basically, and this is the well foundedness of everything. Uh, Now we get full separation. Um, yeah, so well, since we have, yeah, so we get separation. Yeah, for all first order formulas in EPN because they are in fact a special case of the formulas we have separation for in capital W. We're trying to transfer the stuff we have in W down to EPN. Okay, and replacement also can be done fairly easily. This does requires a little bit of the indiscernibility. All right. So after a pretty technical development here, we get um, we get the ZFC axioms, except that at this point we still have to check that infinity holds. Now, the reason why we can get infinity out of this is because we already have a very W is very, very amenable, has plenty of infinity. See, W has a limit ordinal, a limit point, because it's easy to go back and see from the indiscernibility that each of the CNs, CIs, C1, C2, C3, those indiscernibles are all limit points. So we definitely have a limit point. We can just use C of one, in fact. Uh, yeah. Okay. So from that, we can actually we can perform a recursion. So working in W, we can perform a recursion in which we get the integers needed in infinity, but what integers? Integers in the sense of our structure here. See, integers in the sense of our structure here, it's not a matter of being integers in the point. See, we're talking about epsilon connected transitive sets, you see. So we can do a recursion in W and actually build up the integers in the sense of this structure. And then we can argue by indiscernibility that everything is bounded below C of n and we can use this separation in order to get internally infinity inside this structure. So that's more or less how you do that. All right. So we just have ZFC. Now remember, we want to get SRP. We want to get SRP going. Now, let me tell you what we get. What we get is, as n goes to infinity, we get more and more of SRP. So we get, so to speak, we get SRP square brackets n. Actually, we'll get SRP square brackets maybe n minus 3 or something. It doesn't make any difference. But we want to get the large cardinals. So we want to show that each one of these things has pretty strong large cardinals in them, not only satisfy ZFC, but also satisfy there's some pretty large cardinals in there. Okay, that's what we want to do. All right, so let's do a digression into set theory itself to remind us where we're going. How do we do this? The ordinals in set theory are epsilon connected transitive sets. Sn alpha is the set of all n element subsets of the ordinal alpha. F from Sn alpha into alpha is regressive if and only if min e greater than 0 implies f of e is less than min e, just the usual definition of regressive. And alpha is purely n subtle if and only if. Now, this is a definition from this paper of mine in APAL 2001, Subtle Cardinals and Linear Orderings. Subtle cardinals and linear ordering. So alpha is purely n subtle if and only if every regressive function from the n element sets into alpha of alpha into alpha is constant on Sn of e for some e of cardinality n plus 1, living above 1. That's just a kind of pure form of subtle cardinal. So the official definition of subtle cardinal involves taking for every closed unbounded set, blah, 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 blah. You can find indiscernibles in the closed unbounded set. Here, you don't say that. You just say it this way. This is a little better. This is a little easier to work with for what we're going to do. All right. Now, we interpret definition 411.4 in the ZFC model. This set theory definition, this obviously makes sense in our ZFC model. Actually, we go to n plus 3. Any set theory makes sense in any model of ZFC. Okay. So we refer, and we're going to refer this, I don't want to keep rewriting this model with the n plus 3. We refer to this as capital Y. Now, there's a subtle point here. The ordinals of Y are not just the points in the interval, because that's the domain. The ordinals of a model of set theory are not all these sets. The ordinals are special points in here. And this creates an issue that has to be handled properly. This is something that has to be handled. You have to think this through carefully. We want to understand something about what the ordinals are in this structure. And they're not all the points. There's just some of the points. We're going to show that Y satisfies the existence of a purely n subtle ordinal. And preliminary to this, we have to work in W as follows. So now hopping in W, and here's the key idea that allows you to go from indiscernibles to large cardinals. And you can only go from indiscernibles to large cardinals, at least in the level we're talking about, if you have a definable well ordering of things. Otherwise, there's a problem. And that's why we had to had to go to L in section 10. We had to go to a constructible L in section 10. All right. So, and that's what the dollar signs do for us and all that. So if I have a function that's regressive uh, and the constructibility level is below C of n plus 3 of the function, and the function is, yeah, then f is constant on Sn plus 1 of E for some E, for some n plus 2 element E. Okay, so um, the idea is, suppose f is not constant on any such thing, then we choose an f with these properties such that it's least possible. We can find a definable one, and then f is defined without parameters over here. And now we can just look at C1 through Cn plus 2, and they're going to be the answer to the large cardinal statement that we want. So in other words, we're going to assume that the large cardinal statement is wrong. We're going to get a least counterexample, and then we're going to use those indiscernibles to show that the large cardinal thing wasn't wrong there. So therefore, the large cardinal thing was correct. That's what we want to do. Um, all right. So yeah, I think I've set this up. I don't know what. Let's see. F is in here, and I think the dollar sign of one higher place. Yeah. You see, since this is so big, this has to be in. I think that this is what I mean, but it's not a problem. I think this has to be a 4. Uh, yeah. I think this has kind of been screwed up. All right, let me fix this. I think the F is constant on S. Yeah. What I mean by this, I think there's a notation here. Oh, F is yeah. I think this just means an iteration of the power of the pairing function, some simple way. Yeah. Okay. All right. Let me fix it. I think this has to be fixed up slightly. Here, let me fix this up. But the basic idea is clear. All right. Now, um, we have to have an ordinal function. In other words, we need to know, in order to transfer this internally into the structure, into the model of ZFC, this large cardinal thing, we need to know what, given any point in 0 through Cn plus 3, we need to know what element of the structure is that ordinal going to be. You follow me? Uh, yeah. So in other words, as I said, the elements of this interval are not ordinals in the structure Y. They're not ordinals there. Only some of them are ordinals there. But given one of these things, there is a thing called the ordinal associated with it in Y. And this mapping is constructible, is a mapping that's handled in the system. And it's an isomorphism. In other words, this is less than this if and only if this is less than this. This is less than this if and only if this is a member of this in the sense of Y. Where we're talking about actual ordinals in the sense of Y. And the initial segments are also handled. exist and all that in the structures. All right, so uniqueness is simple. The existence is the issue, and it's the kind of transfinite recursion we've been doing that will work for this. In fact, it goes back to 411 too. Remember where we did our first kind of transfinite recursion, where we enumerated the elements of a set transfinitely, of a transfinite set. All right, this goes on for quite a while. I put it all down here, but we don't want to really go through that. All right, now finally we get that the structure satisfies that the ordinal associated with C of n plus 1. Now remember, this structure goes all the way up to C of n plus 3, is purely the ordinal associated with this point is purely n plus 1 subtle. And we work in the structure and we assume that we have a mapping internally in the structure that's a regressive function in the sense of y, and then we shift it back into actual points inside W using the ordinal map. We push it back into points, sort of like ord inverse. And then it becomes, in the sense of W, pushing it back into W, it's regressive and defined. And then we get, because of the large cardinal idea that we proved holds in W, we get an E, which is the indiscernibles that we want, and then we go back to Y, and we see that B is constant on the ordinals that they represent. So this requires you to go back and forth between the structure Y, which satisfies EFC, and W, the part of W that lives below C n plus 3. And we get that this particular, the ordinal in Y corresponding to C of n plus 1 is a large cardinal of the kind that we want. Okay, then we get that SRP is consistent because n is arbitrary. We get a purely n plus 1 subtle ordinal inside the structure, this structure, which we call Y. And so Y satisfies the existence of an ordinal with the NSRP, because in this appendix from the paper in 2001 I cited that I wrote, purely subtle ordinals give you SRP cardinals. Okay, so we have a purely n plus 1 subtle cardinal, we get an NSRP cardinal. And since n is arbitrary, and remember these n's were standard, these are standard, we get that every finite fragment of SRP is consistent, therefore SRP is consistent. Okay, Andreas, I'm done.